So I'm going to have to back up a little bit, because I'm just jumping right into it, but I'm going to back up talking about stoichiometry. So far, the stoichiometry types of problems that we have, there's a driving force. If there's a driving force present, and we say there's reaction, and if there's reaction, then we can do our standard stoichiometry. Stoichiometry will tell us, how many moles or how many grams or how many liters of product are formed. If there's no driving force, let's say the driving force were in the reverse direction, and then we say no reaction. If there's no reaction, then there's no need to do any stoichiometry. Basically, we can use the basic concepts of stoichiometry. When we look at this energetically, a driving force means that the products are much more stable than the reactants. So let's say I had the reactants up here. This is where I'm starting, and then the products are here. So as I'm moving from reactants to products, I see there's going to be a drop in terms of energy. I'll put energy on the y-axis here. And so if the products are more stable than the reactants, then we expect a driving force. And the same thing if there's no reaction, maybe the driving force was predicted in the reverse direction because the reactants are more stable in this case. So we'll put the reactants down here. And then as we go to products, products are going to be at a higher energy, therefore they're more unstable. So it goes like this. This is going to go like that. But what happens if the products and reactants, there's not much difference in the stability? So let's say, what happens if the reactants are here and the products are just slightly more stable than the reactants? Therefore, there's not a significant difference between the reactant stability and the product stability. Likewise, what would happen if the reactants are here and the products are a little bit less stable? Just a little bit less stable. Here. Or what happens if they're the same stability? If we look at the reactants, compare it to the products, they're at the same level. What happens is, either we have reaction or no reaction. In these scenarios, what we're going to have is partial reaction. Partial reaction is going to be given by, having the forward and the reverse arrows like this. And this is what we call an equilibrium. What they mean by an equilibrium is we're going to have an equilibrium that's going to exist between the reactants and the products. Over here, there's not much of an equilibrium because it's totally lopsided. If we look over here, it's all products. The products are much more stable. Likewise, over here, it's all reactants because the reactants are much more stable. But in scenarios like this, where it's not clearly favored in one direction or the other, there's going to be an equilibrium between the reactants and the products. In this bottom scenario, it's going to be kind of evenly split between reactants and products. The top scenario here, all these are going to be represented by equilibrium like this. Actually, writing it like that. Just the arrow. The top one, the products are just slightly favored, not hugely favored. If they're hugely favored, then we'd expect all products no more reactants. But the products are just slightly favored. In this middle one, the reactants are slightly favored. And so what that does is it means that our stoichiometric predictions are going to be messed up. They're going to be messed up because we don't have full reaction or no reaction at all. We have partial reaction. And so what do we do with the stoichiometry for partial reaction? We have to use a different method in doing the stoichiometry for these problems. And so if we have partial reaction, what I mean by this is partial reaction is not, in a point of time, this is partially reacted on its way to full reaction. No, this is partial reaction and then it's stopped. If we have partial reaction at what we call equilibrium, equilibrium being the end of the reaction, so you've waited and you've waited and you've waited and still no more reactions taking place, then we call it partial reaction. And that's as much reaction as you're going to expect because nothing's going to change macroscopically. So if we have partial reaction at equilibrium, then with stoichiometry, calculations must be done differently. All right, so let me give you some examples of this, just using a water analogy here. Here, I'm going to put a water in a U-shaped tub like this. On the left, the tub is a little smaller than on the right. When I fill this with water, let's put like 50 gallons of water in here. If I put 50 gallons of water in here, okay, what I'm going to see is that I'm going to see that the two water levels are going to be equal at equilibrium. Yes. And that there's going to be no further change in the height or the level of the water here. And so this is a system at equilibrium. At equilibrium, looks like no change, but there is some change. There is some change in that the water molecules can go. So water molecules can move left to right. But at the same time water molecules are moving left to right, water molecules must be moving back right to left. So for every one molecule that moves to the right, one molecule has to move to the left. Otherwise, if we have all the water molecules moving, then all 50 gallons would just be on the right side here. And so this is a situation at equilibrium. However, which side is favored in this? Is the product side favored or the reactant side favored? What I mean by this is which side has more water. If I look at this, which side has more water? The right side has more water. And so what we say is the right side is more favored. There's more water on the right side. And so, in other words, over here, this is the same type of scenario. The products are favored here over the reactants there. So that would be at equilibrium. But the equilibrium might look different. If the reactants are favored, the equilibrium might look like this, where the left side now has most of the water. If the left side has most of the water, there's still 50 gallons of water, let's say. But if the left side has more water, then this is a scenario where the reactants are more stable. We'll call the left side the reactants, I forgot to do this, and the right side the products. And it's the same over here. Reactants on the left and the products on the right. So here's a scenario where the left side is more favored, therefore the reactants are more favored in this case, but it's still what we call a dynamic equilibrium. It's at equilibrium in the sense that the water levels don't change, but it's dynamic in the sense that water molecules keep moving back and forth. And so this would be at equilibrium. But it's a different equilibrium because in this case, the equilibrium is favoring the reactants. And the final scenarios is, where the reactants and products will have the same as well. So this would be at equilibrium as well here. All right, so equilibrium is a closed system and dynamic in nature. It's reversible. It's reversible in the sense, okay, water can move back and forth. All these are reversible. Water can go left to right or right to left. There's no problem with that. It's closed in the sense that we aren't adding water. For example, we're 50 gallons, just distributing it differently. And so that's how it's closed. If we started pouring water in one side, it's going to impact things, or if we start removing water, it'll impact things. A closed system means we aren't adding or removing anything out of the reaction. This is just water moving from left to right. It's dynamic because we continually have movement to the right and movement to the left. This is the dynamic equilibrium here. We've seen dynamic equilibrium before with vapor pressure and other things. This is the applied to chemical reactions. Some chemical reactions are easy to reverse. Some are difficult to reverse. And so when we have partial reaction, oftentimes what we have is just a reversible reaction. A reaction that can go forward and reverse. In this case, it can go reverse because it's not so high up. In other cases, it can't really reverse because it would cost too much energy. So there's a huge energy drop down, but to climb back up that hill would be a lot. So here, okay, there's a little energy drop down here, but there's no problem here. I'm going back, and the same thing here. And this reaction is reversible, and this is obviously reversible because they're at the same level. And so this would be slightly downhill going backwards. This would be slightly uphill going backwards. I'll show you how a reversible reaction. What types of reactions are reversible in nature? This is a reaction here. This is kind of a complicated reaction because this is mixed. But it's a reaction in which they're taking calcium ions with bicarbonate to form calcium carbonate and some CO2. There's two reactions that are occurring here. Sometimes that happens. There's competing reactions and side reactions that can occur. Okay, so this is calcium with bicarbonate, forming calcium carbonate and CO2. Here's another reaction. This is a reaction of calcium carbonate with CO2. If they take calcium carbonate and bubble CO2, then they can form calcium ions bicarbonate, so they can just reverse the reaction. And so this reaction can go both ways. If the reaction can do that, then we're going to strike some kind of balance. There's going to be a balance where it's not going to be all product or all reactant, but there's going to be a mix of product and reactant, like here. So this slide is a little bit confusing, but we can just skip it. It makes sense that there could be a mix of product and reactant when we see how the reactions occur, what we call mechanistically. And how these reactions occur. And this chapter is actually two topics in chemistry. The two topics in chemistry are kinetics, reaction speed, and thermodynamics, the stability of the reactants and products. Normally we don't take those together. We treat those separately, but in this chapter we're going to take them together. So the first part of this is just looking at how reactions occur and how fast they occur. So this is collision theory. Collision theory is just quantum mechanics applied to chemical reactions. Okay, in order for something to react, there has to be a collision. And these are the particulate level. We saw this before. Here, let me show you. This is a slide from chapter 17, the acid chapter. And what happens is these two waters can collide with each other. if they collide with each other, then they can react. So for example, one water acts as the base, the other acts as the acid. So here we have the base, here we have the acid. The base is a proton extractor. The acid is the donor in this case here. So proton acceptor, proton donor is what we call it. And so we formed this. Now which side is more stable in this particular equilibrium? Okay, so what we do is we just let the water sit, and then just wait until things have stopped reacting. And so which side is favored in this particular, which side is more stable, water or hydronium and hydroxide? Which side is stronger acid, stronger base? What's the stronger acid, water or hydronium? What do you think? All right, well, how about the bases? Which one is a stronger base, water or hydroxide? Yeah, hydroxide is a stronger base. We don't even need the chart for this, but you can always look it up on the chart as well. But hydroxide, like sodium hydroxide or whatever, is going to be a much stronger base than just water. And so this side is stronger, this side's weaker. In other words, something like this. Water, and water. And this is going up a lot in energy because we're forming hydronium and hydroxide. It's quite unstable. And so this particular reaction heavily favors the reactant side. The reactants are much more stable than the product. And the more heavily favored, the less reaction we expect. In fact, we could say no reaction because there's no driving force here. And normally we would say no reaction. We say no reaction because we're going from weaker acid base to stronger acid base. Weaker to stronger is not a driving force, so no reaction. But when we look at how reactions occur, a little bit of reaction can occur. How come a little bit of reaction can occur in this particular instant? Because even though this proves to be a huge energy barrier, for most of the molecules, there's a tiny, tiny fraction that have enough. So if I have 1 billion water molecules, there's a tiny fraction out of that 1 billion water molecules that actually has enough energy to react. It's going to cost a lot of energy because you're making very unstable products. In other words, there's going to be violent collision here. This violent collision is going to result in the formation of some hydronium and some hydroxide. In other words, bond breakage and bond formation. About how many? If I had 1 billion water molecules, about how many of those have enough energy to climb that huge hill? Yeah, just because we say no reaction doesn't mean that there's no reaction. It's just a qualitative thing. Just because we say something is soluble does not automatically mean it's infinitely soluble. Like sugar. How many sugar cubes can you dissolve in a cup of coffee? Well, it's soluble. Sugar is soluble. Therefore, you must be able to dissolve an infinite number of sugar molecules in coffee. An infinite number of sugar cubes? No. But we say it's soluble. Just because we say there's no reaction doesn't mean there's absolutely no reaction. There might be a tiny bit of reaction that occurs because of collisions. And those collisions, unfortunately, we can't stop those, you know, but they're highly unfavorable. The bigger this energy barrier, the fewer the collisions are, and the more we're okay. I mean, in stoichiometry, if we did this using our standard stoichiometry, we'd say nothing reacts. And be done with it. However, in this case, it's important to know that tiny fraction that does react. The tiny fraction that does react comes from a curve like this. There's a little tail at the end of this curve. You remember seeing something like this? Where we plot, do you know what's plotted here on the y-axis? Curve like this look familiar at all? What's plotted on the y-axis? Not the temperature. It's something else. I did put the temperature there because temperature is important. Temperature is really important, and so temperature would be like a third dimension on this curve. The two dimensions on the page would be